Hello and welcome to Matt's Garage. Well, hello and welcome to Matt's Garden Shed. You might remember last year we built the garden shed. It's really worked out great. It's gone through an entire year. It's perfect winter, spring, summer, and fall. And you might also remember that I hinted at putting solar power into the shed so that I can get basic electrical service here. And well, we did it. We have solar power powering this garden shed. So what I'd like to do in this video is walk you through what the system is, how it works, and how it powers my shed. Let's get to it. All right, so let's take a look at the system. If you don't know anything about solar powered electrical systems, this will be a little bit of a tutorial, but it's in no way a real full DIY on how do you put together this system yourself. There's plenty of other videos on that topic that you can search for. What I really want to show you is what this system is, why I chose the parts that I did, and a little bit about how it works. So let's start with the battery. I chose to go with a 24-volt system. There's a number of voltage levels you can use for a typical solar system. There's 12 volts, 24 volts, and more popular 48 volts. But for this system, I decided to go with a 24-volt system. So, of course, you are looking at the battery and it says 25.6. Well, 24 is a round number. So this is a 25.6 volt, 200 amp hour battery. And that gives me more than enough power to power this shed under most load conditions. So a battery itself is not enough. So I actually have an inverter. And what the inverter does is it takes the direct current, DC current from the battery, and converts it into alternating current, the kind of current that runs your typical lights and the outlets in your home, or in this case, in the shed. So starting from the battery, there's a couple of connections. One I connect, and you might not be able to see it perfectly here. I connect up into a fuse. This is a 200 amp fuse, just to protect the system downstream and also to protect the battery from any surges. On the negative side, I connect to what's known as a battery shunt. It is a monitoring system for the battery. And my particular shunt is from a company called Victron. It's their smart shunt. And there's a very nice Bluetooth app that I'll show you a little bit later that it connects to that gives me some information about the state of the battery. From the shunt, I go up to the negative bus bar. Just a convenient way of grouping all of my negative connections together. Similarly, from the fuse, on the positive side, I go up to a battery switch. That lets me cut off any power from the battery up into the rest of the system if I need to do some work on it. And it, in turn, also goes to a bus bar, the positive bus bar. So at this point, we have power coming from the battery, going through a fuse and a switch on the plus side, going through a little monitor, and up to the bus bar. Let's start with the inverter then. From the bus bar, we connect the positive to the positive side of the inverter and the negative to the negative side of the inverter. If I didn't have anything else, if I didn't have solar or anything else, this would actually work. And in fact, if I wanted to, I could turn the solar off and this would produce electricity just fine. In fact, the overhead light, and we'll show that a little later, is being powered by this inverter right now. So this inverter produces 3,000 watts of power. It claims to peak higher than that, although I've never actually gotten it to go into peak power. But it's more than enough for what I need in here to charge some tools, to run the lights. My pellet grill is over there, so I've actually run the pellet grill off of shed power. So it's a pretty solid inverter. Going into the other side of the bus bar is the power from the solar controller. And the solar controller's job is to take the somewhat uneven, unreliable, erratic power that comes from the solar panels and convert it into something that can be used in two ways. One, to charge the battery, and two, to be consumed if needed directly by the inverter. So it does its job very well. So far, so good. On the way off of the bus bar, I do go through a uh, a 40 amp breaker on the positive side, coming back from the charge controller, and going out from the charge controller out to the solar panels. There is also a DC circuit breaker, and that's so if I need to work on the system, I can turn off power from solar. I can cut power from the charge controller to the rest of the system, and at that point, no solar whatsoever is making its way into the system. It's just battery and inverter. You'll also notice here that I have a little transformer. Because this is a 24 volt system, I did purchase and install a 24 to 12 step down transformer, DC transformer. And here's a little 12 volt fuse box here. And that's in case there are any 12 volt appliances, like my ham radios, for example, that I want to run off of shed power. I will be able to do that. All right, at this point, we've covered everything that generates the power. Next, let's take a look at how we utilize the AC power that comes out of the system. And we're going to do that right now. Okay, we've seen the basic layout of the system. Now let's take a look at how we actually utilize the power from the inverter to power the shed. The inverter, as I mentioned, puts out 3,000 watts. It's a 120 volt system, so I couldn't power any 240 volt appliances, which I don't have to do out here in the shed. And it has a couple of outputs. It has two outlets, which I don't use, but importantly, it has a terminal block with a hot, neutral, and ground. And so I've run a 10 gauge two wire, I should say, cable from the inverter up into the service panel. 3,000 watts, approximately what you want to use a 30 amp breaker, round numbers. Inside the breaker panel, and this is a main lug panel, really designed to have the main somewhere else, I install a 30 amp breaker, and I feed the hot over to the bus bar that 30 amp breaker is installed to. And then from the screw terminal output of this breaker, I send it to the other bus bar. So power comes into one bus bar and comes out and powers the second bus bar. So these two breakers for the lights and the outlets are just standard service circuits, and they have a main that protects them. Inside the box also, there's a neutral bus bar, and there's a ground bus bar that I've installed, and neutral and ground are bonded together. And the reason why I bond them together is because this particular inverter has a floating neutral and floating ground. Inside of the inverter itself, they are not bonded. And that's pretty typical for these sort of inverters. They're used on boats and RVs and things where you don't really have a real ground. But since I do have a real ground, since I pounded a ground rod 8 feet into the ground outside the shed, I did some tests and convinced myself that grounding and bonding at the panel was not only safe, but appropriate. And that gives you a lot of good things. One is that you have a good ground. So if there are any stray currents, if something has a fault in it, there's at least a fighting chance that that current will make its way over to ground. And second, it means that the GFCI circuits are operating properly. If you push the test button on them, they absolutely work fine. And second thing is that if you plug a standard outlet tester into these outlets, they show as wired correctly, which is really what you want. So pretty standard stuff. And in the next part, we'll take a look at the actual wiring of the shed. Nothing too fancy, but I want to just walk you through that. So let's go do that. As you can see by my very careful labeling, we really have two circuits. The light circuit, which feeds this light right up here. So I run the hot right up to the box. And then from the box, I run 3 wire back to this switch. Just a standard switch, but I ran 3-wire because to code modern code anyway. You should have a neutral available in every switch box. So in this case, the neutral is just tied off. It's not doing any real work. You also see that I have an outlet right above it, and that's fed by this this 12 gauge wire. I think I did a reasonably good job of getting the wires up through the rafters, et cetera, et cetera. So this is a GFCI, so it's fed by, again, a 20 amp circuit, 12 gauge wire. The second wire coming out of it makes its way back all the way over and down here. And this is on the load side of the GFCI, so it is in fact also GFCI protected, but you don't need to use a GFCI outlet everywhere. You can, but I had this one laying around. It has some USB in it, so I have actually charged this phone off of this outlet. The system works great so far. So let's, hey, you know what? Let's take a walk. So we're going to walk over to the solar panels. So I've got 2 solar panels here. These are both 200 watt panels. I had bought the first 200 watt panel, I want to say the lower one, well over a year ago. It was at that point what was called on sale. You can get the same panel for a little bit less these days. And then because I had, sort of mid project in some sense, switched to using a 24 volt system, and because I learned a little bit about my charge controller by studying it, turns out that I really did need more voltage in order to activate the charge controller. So these two are wired in series. So the nominal voltage of each of them is right around 20 volts. That means the total voltage is about 40 volts. And you need to have the voltage coming from the charge controller to be about 5 volts above the battery voltage. Otherwise, the charge controller won't engage and it won't turn on. It won't start charging. So that was a bit of a lesson learned. But I had already built the solar cart here, and it's a very simple design. So long story short, these 2 panels give me, with the sun shining on them, about 40 volts, somewhere in the neighborhood of about 10 amps or so, 10 or 11 amps. And again, they are wired in series. I use the standard, I think they're called MC4 connectors, and that makes its way all the way over to, we were getting a nice view of the apple tree. The apple tree's doing very nicely this year. All the way over to the side of the shed, where I put a fairly standard Cantex box that one purchases from Home Depot, some weatherproof glands, and ran the ground wire out through one of the glands. I may actually change that and either get another gland or just drill a small hole for the ground wire. Technically, I don't think you should really have the ground coming out the same gland as your PV input, but for now, it's not causing any problems. So that's the basic lay of the system. What we can do next is take a look at the power capabilities. And the nice thing about that is that the apps have very good data. They store historical data. So let's take a break, and when we come back, I will show you a little bit about how much power I'm actually generated, how the battery charges, and a little bit about how it works on load. Be right back. So this is the Victron Connect app. I did a screen recording of this, so apologies in advance if the audio isn't as crisp as it normally is in my videos.
and it shows information about both the battery and the charge controller. So we'll take a look at the battery first. You can see right now it is 100% charged. We're going to connect over to it. It does take a few seconds sometimes to connect. I've noticed that the Bluetooth signal from the shunt isn't nearly as strong as from the charge controller, but it eventually catches up. And you can see here that the battery is approximately 100% charged, and it's got a nearly full voltage, 26.5 volts. It is drawing 2 amps and 55 watts because I have two lights on. I have the overhead light on, and I have the light from my recording stand that you might have briefly seen earlier in the video. So if I turn the recording stand light off, let's see what happens. And there we go. It dropped down to about 1 amp draw and 27 watts. Now the unit itself consumes some power, but you can see here some historical stats of how much charge has been drawn out of the unit, how much it's discharged, how much it's charged, how long it expects, how long since the last charge. So a lot of useful information. Now, if we look in the solar app, the charge controller app, we can see two things. One is that it goes a lot faster, and we see some basic information. Right now, it's evening, so we don't have a lot of sunlight right now, so we're not really getting much charge. Just sort of nominal, pretend charge going into it. Um, but the neat thing about this app is the history. We do get to see what yield came from the unit. So today, for example, it looks like we got about 610 watt hours, so a little over half a kilowatt hour. And remember, a kilowatt hour is if you had 1,000 watt light bulb and you ran it for an hour. That's a kilowatt hour, and that's typically what your power company charges you. So a typical average day, it's been fairly sunny these days. I get somewhere around that 600 or 700 kilowatt hours. These short days here are actually part of one day where I actually had to shut the system down because I was doing a little work on it. But there's, a 700, a 600, an 800. I think on one very sunny day when I was doing load testing, there it is. I was really drawing a lot of current, running the vacuum cleaner, running the heat gun a little bit. Um, and it did draw the battery down. It was a very sunny day. It sucked up 1.2 kilowatt hours. So I was very happy that the solar panels have been able to provide me with this level of power. It's really been fairly impressive. So that's just a little bit about how the app works. I do like it, it's very handy. But at this point, I want to wrap up and just tell you a couple of things that I like about the system, a few things maybe that I don't like, and a couple of things that if I had to do it over again, I would change. So stay tuned.
So let's wrap up. Hopefully, you got a lot out of this video. We've gone through the basic components that I use to build the system, a little bit about how it works, took a walk over to the solar panel, said hello to the apple tree, and gave you a sense of how the whole shed was wired up. What would I do differently? I think I would probably have gone with a 48-volt system. A 48-volt system is going to be a little bit more efficient. I can use smaller wires coming off the battery, smaller wires going to the inverter. More voltage means lower amperage. So even as it's drawing power for loads, the amount of amperage coming off the larger 48 volt battery is going to be half, round numbers, as much as would be coming off of the 24 volt system. So that's one thing I would do differently. Another is that given the cost of all the components here, and they're not inexpensive. The inverter is at $250, and the charge controller was, I forget, it might have been approximately in that range. And there's breakers and bus bars and things like that. Today, a 3,000 watt so-called all-in-one system is a lot less than that. I could get a no-name off-brand one for probably about $250 these days. So I could almost buy two of them for the amount of money that I put into all of this. And I could get a pretty good name brand one for about the same as I put into this system. And what that does is a couple of things. One is, it certainly it makes it look a little less, little less hillbilly. And second, it is a little bit safer. There's a panel that hides all of the wires. You don't see any of this stuff. Your bus bars, your breakers, all of that are built into the system. You really have, power coming in from the photovoltaic cells. You have power going out and in from the batteries, and you have power going out feeding your service panel. And it's done nice and clean. It's done like a proper electrical service appliance. So I would probably do that. And in fact, I'm very likely going to start another project around putting proper solar on the garage. I think we might make the garage as close to off-grid as we possibly can. And so I'd certainly be using an all-in-one system there and a more sophisticated battery system. But that said, it seems to handle loads fine. The current load of just running the light and the light from for my filming light, it's barely making a dent in the battery. I could probably run those for a week straight before I drain the battery. And as long as the sun was out during those days, the battery almost certainly would charge fully up. I haven't run a lot of proper real use loads. I have had to use the vacuum cleaner in here. I do vacuum up from time to time, and certainly when I was drilling the holes to route all of the electrical wire, I created a lot of sawdust and chips, and so no problem starting up or running the vacuum cleaner. And it's a bit of an old school vacuum cleaner. It draws easily 5 watts on startup. I looked in the app as it was running. It was certainly drawing close to 1,000, 1,100 watts while running. Excuse me, there was a fly on my leg. So under sort of normal in the shed load, no trouble. I haven't pushed it and done the sort of tests that some other people have done, where you have 27 heat guns and see which one of them causes the inverter to trip. Frankly, I don't want to see what happens when the inverter trips. I know it'll eventually trip if I really push it hard, but for now, I've got lights. I can charge the weed whacker. I can run the shop vac. I can power the pellet grill. So it's doing everything I need it to do. That said, hope you enjoyed this video. Please make sure to subscribe to the channel so you can get more content from Matt's Garage. Please make sure you like this video if this is the kind of content you like. Helps me, helps the channel, helps the YouTube algorithm. All right, that's the Solar Shed project. See you in the next one.